Welcome back to the classroom. My name is Mr. Wong. Today we'll be looking at different types of acid reactions. Before we talk about the way acids react, I want to talk about the concept of strong and weak acids. Now, last lesson we talked about the concept of pH. pH representing the amount of hydrogen ions. Hydrogen ions is H+. In actual fact, it's also just measuring protons. So this is a measurement of how much concentration of H+ do we have in a solution. We said that if it's a pH of 1, we have the highest amount of hydrogen ions. And then if we go to 14, we have the lowest amount. In this image, 12 is the lowest one we have, so in this case, this one has the lowest amount of H+ ions. The one thing we need to take into account though is pH, or concentration, isn't a true reflection of whether or not an acid is strong or weak. If you look at the image that we have on the left here, it kind of portrays what we mean by strong or weak. Now, what actually happens in acids when it mixes with water is, if it's a strong acid, it will release all of its H+ ions in the water. So that's if it's strong. If it's weak, it will only give a small amount of hydrogen ions. So in this case here, our transition from here to here, this is an example of weak ion or weak acid. You can see because we only have a very small amount of ions being released in the water. Okay, so a small proportion of molecules give up their protons. That's what we mean by a weak acid. Example of a weak acid would be citric acid. So that's the acid that you have when you eat fruits like lemons, oranges, things like those. If we are dealing with a strong acid, the the ions will behave slightly differently. If you can actually see here, the transition that we get is these ions fully breaking apart from each other. So these ions that we have here, they're breaking apart and they are becoming more individualized. So if it's a strong acid, they give up most, if not all, of their protons. Okay, so that's the difference between strong and weak acid, and the difference when we say concentrated and low concentration acid as well. All right, let's look at the different types of reactions you can have with acids. You can have acids reacting with bases. We talked about what bases were. We can have acid reactions with carbonates. An application you can see is in baking, and then we have reactions where acids react with metals. Let's go into the specific ideas for each one, and then we'll see where and how do we know if it's happened. Okay, so neutralization reaction. You can see we have an acid, hydrochloric acid here. You can see how it's dissociated into water. You can see me introducing a base, in this case, sodium hydroxide. Okay, so there's that. You can see we formed sodium ions and chloride ions here. That forms the salt. Okay, but focus on the hydrogen, the H+, the protons, and the hydroxides. They actually get attracted to each other and they form water. Okay, so we can see there's two things that are happening here. One, we're breaking the bonds between the acid and the base, and then the hydrogens from the acid will react with the hydroxide from our base example here. Okay, you can see they attract with each other to form water. Okay, so just another demonstration of this diagram image here to show the net reaction of a neutralization is to form water. So what is a neutralization reaction? A neutralization reaction describes acids and bases. You can almost say they cancel each other out to form an ionic compound, which is our salt and water. So the example we had before was hydrochloric acid reacting with sodium hydroxide to make sodium chloride. This is table salt. Okay, so it's the salt that you can eat. This one here, table salt. And we get water. If you actually notice this symbol here that says aqueous solution, remember aqueous represents it's dissolved in a solution. Now the best way to describe that is if we go back to the simulation, you can see the way we demonstrate it's dissolved is the ions are separated from each other. They're not connected. Whereas if you look at water here, it is in its liquid form. That's because it's pure, it's bonded together. Okay, so let's just look at that simulation again, and let's just talk about the process of neutralization, which is the acid plus the base canceling each other out in a way. Okay, for the acid in our example here, the component that's going to be cancelled out is the H plus. For the base component, it's the OH minus. There are other ways we can identify bases, but let's just say for now, bases are hydroxides. Okay, so back to our simulation. I'll just let it flow around. You can see how the ions are not connected to each other, so that's why it's aqueous. Okay, so we see the hydrogens. Okay, it's in aqueous because it's separated. You can see now it's going to cancel out with the hydroxides. So at this process now, we have a complete neutralization. So the chemical is no longer high concentration of H plus or high concentration of OH. They have essentially cancelled each other out, and that's what we mean by neutralization. Okay, so how do we know if a neutralization reaction has occurred? The best way is to look at the pH changes. We know that for an acid, their pH is always smaller than 7, whilst the base is always higher than 7. Okay, the solution, when they combine together, that pH will be anywhere between the difference between the acid and the original base. We did say water has a pH of 7, and if we have one strong acid, one strong base, we might get a pH of 7 here, so it turns green if we use a universal indicator. You can see with the acid, it's pink, the base is blue. Using our universal indicator, different colors we can get. If you recall, the universal indicator is just a way of looking at how acidic or basic something is. So that's one way. If we see a pH change between the two, okay, and also a color change if we're using an indicator. That's not to say all acid-base neutralizations will have a pH of 7 at the end. It does depend on if you're using a strong or weak combination, but we don't need to stress on that. We just need to know in a neutralization reaction, it's an acid plus a base, makes a salt and water. Now, where can we find applications of neutralization? You can have toothpaste. So your toothpaste is built up of a base that will react with the acid that is enabled on your teeth, enamel, due to bacteria producing acids on your teeth, and this actually neutralizes the acids on your teeth, and that helps preserve oral health, which is why you need to make sure that you should be brushing your teeth after every meal you've had. We have bee stings, which exerts an acid called methanoic acid. You can actually use lime water to help neutralize it. Lime water is a base, calcium hydroxide, or calcium hydroxide, and so that's what you get there. We have wasp stings. So wasps actually exert a venom that's highly basic, so it has a pH higher than 7, and you can use acid to kind of neutralize it like that. Another one that people tend to do is, if they're eating really spicy food, is to drink milk. Now milk is still acidic, however it has a much higher pH than most chilies, so that's kind of the solutions people tend to use instead of using water sometimes. Right, next one we have is acid carbonates. Now, carbonate, the actual ion, is CO3 2-. That's a carbonate we're dealing with. So we're looking at how acids, the hydrogen, will react with the carbonate here. Okay? So that's what we get. We still will get a salt at the end, but we get different formations. We get carbon dioxide and water forming in this reaction, and then we get the cations and anion solutions forming. So let me just show you what that means. Okay, so the general formula to describe an acid-carbonate reaction is the acid will react with a metal carbonate to form a salt. So remember, if it's a salt, there is a metal and non-metal component, or another way of saying it, we just form an ionic compound. We get carbon dioxide, which is CO2. That'll be as a gas. And we get water, H2O, as a liquid. Let's look at the example down here. If we have copper 2, this 2, remember, represents the charge number. So copper 2 carbonate is reacted with hydrochloric acid to form a salt, water, and carbon dioxide. So we are forming these three things, hence that's what the arrow is representing here. We have copper 2 carbonate, this is here. For those who want to know how we get that, copper is 2+, carbonate is CO3 2-. You can see the valence charges, or the charges that we have here, are identical. So you just combine the two symbols together, and that's what you get. We have hydrochloric acid and that. So we have water, we have carbon dioxide. How can we work out the salt if I didn't tell you this was the formula? Well, firstly, the hydrogen atom will be used to form water, so you can assume that's been used. We know that the carbon and the oxygen, that's going to be used to form water and carbon dioxide, so that can be excused as well. So you're only left with chloride and copper. Those are the only things that haven't reacted. So these two are the two ions that combine together to give you this, copper chloride. Take notice that this is aqueous, which means it's dissolved ions. So the copper and the chloride aren't actually connected or combined together, they're actually dissolved in the water as their ion forms. Like so, if we were to write it like that. Don't need to get how we write that, just appreciate the fact that AQ just means they're not actually combined together, they're dissolved in water. So, an application of acid carbonate reactions is using baking soda when producing bread. So, in self-raising flour, we have an acid called tartaric acid, and also some sodium hydrogen bicarbonate, or carbonate, which is baking soda. When you put this in an oven, the heat actually allows for this reaction to occur, so it needs heat to cause this collision to occur. In that process, hydrogen or carbon dioxide is released, and that actually causes your bread to rise, and also gives the texture of the air bubbles when you eat bread. So this is the importance of acid carbonate reactions. And obviously there are many more. You have reactions with acid rain. So with the a lot of sculptures in medieval times used limestone, which is made out of carbonate. And when you react acid with limestone, that's where you see the defacing of sculptures. One way of working out if we have formed a acid-carbonate reaction is testing for the existence of carbon dioxide. So, if you have carbon dioxide, filter it in a test tube of lime water. Lime water is made out of a chemical called calcium hydroxide. If you react that carbon dioxide with the lime water, it forms a reaction known as precipitation to form a white precipitate called calcium carbonate. So this is what the transition you would see if there is carbon dioxide reacting with the calcium hydroxide. So I might just write that down. So this is calcium hydroxide, and then we form calcium carbonate here. Okay. Well, you can actually see this precipitation and neutralization are examples of a double displacement reaction. So this is how we can actually test whether or not we have an acid metal carbonate reaction forming here. We call it the lime water test. I know I wrote carbon dioxide test, but the actual technical name people call it is the lime water test. Okay. Next one we have is the reaction between acids and metals. You can see here we have aluminium reacting with hydrochloric acid. You can see there's a lot of steam forming here, and that's to demonstrate that it's a exothermic reaction. You can see it's really hot and very vigorous. So what's actually happening here is when you have an acid reacting with a piece of metal, again, you form a salt and you form hydrogen. In this case, hydrogen gas. So the example we use here is hydrochloric acid. So hydrochloric acid reacts with magnesium, which is a very reactive metal, and that forms magnesium chloride. Whoops, just get rid of that. So we get magnesium chloride, and then we get hydrogen gas forming here. The metal is obviously solid when we react it. We use diluted acid to do this reaction, so not concentrated but diluted. The reason being is if it's not diluted, the particles can't actually separate and then react with the metal. So there is that. One of the things I might want to mention is acids are really good at corroding metal if it's diluted, but not all metals. If you actually have a look at this chart we have here, or even this image here, not all acid metal reactions are equal. You can see some are really fizzy. That fizziness comes from the production of hydrogen gas, and then some don't really react at all. And that comes to this reactivity list that we have here. Quite similar to something we talked about with corrosion. Different metals are more reactive to acids. Potassium is one of the most reactive with acids, and then gold and platinum and silver are very non-reactive. Again, which is kind of why silver and gold were highly prized throughout history, because of their lack of reactivity with most of the elements on the planet. Okay, so how do we know if such a reaction happened? That's through a thing called the hydrogen pop test. So when hydrogen is highly flammable, if you expose it to a flame, what we call the pop test, there is going to be this pop sound. That pop sound comes from the reaction between oxygen and hydrogen to make water. One easy way to do it is if you have two test tubes, when you react the acid with the metal, you cap another test tube on top because hydrogen gas is lighter than air. So when you do this reaction, the hydrogen gas is going to rise up. Okay, so if you have a test tube capping on top of the other test tube, you can actually lock the hydrogen away. So when you do that reaction, you have all this hydrogen gas at the very top component of your test tube. When you introduce that flame, you get your pop reaction there. In that process, you'll see sort of a little flame forming, and that's just to represent the chemical reaction of hydrogen and oxygen occurring at that particular point in time. An application of acid metal reactions is actually through portable batteries. So the lithium ion batteries actually uses the acid as a way to allow for these ions to move along the cell, and this actually helps conduct electricity. So that's kind of the application we can use there. Alright, and that kind of concludes our lesson for today. Thank you so much for watching up till now. Hopefully you get a better understanding of the 3 different types of acid reactions, and give this video a like to support future videos coming out as well. Thank you for listening.